Hey guys, it's time for Lesson 13. We're going to be applying some of the things we've learned about perturbation theory to a few situations that we sort of left from the hydrogen atom, but we didn't deal with. So the theory of the hydrogen atom that we used last semester ignored the fact that the speed of the electrons is borderline relativistic, and the fact that the electron in the hydrogen atom has a spin and an associated magnetic moment. And as a result of having a magnetic moment, it can interact with magnetic fields. Now you might think, well, there's no currents around, there's no sources of magnetic field around, so what relevance does that have? And the answer is, in the frame of reference of the electron, there is a magnetic field. And the magnetic field comes from the electric field of the proton. So we'll talk about that more in a minute, but let's start with the relativistic correction. So it turns out that the kinetic energy that we used to solve the hydrogen atom looked like this. It's the classical kinetic energy, p squared over 2m, and it's wrong. It's wrong because the actual kinetic energy is the total relativistic energy minus the rest energy. And so we ought to use this expression. Now there's a way to do that, which is you cook up something called the Dirac equation and you solve it. But that's way beyond the scope of what we're going to do this semester. So one way to deal with it is to say, well, what if I treat that square root as a power series? So what I'm going to do is notice that the square root of 1 plus x squared you can expand as a Taylor series, and it's 1 plus x squared over 2 minus x to the 4th over 8, and so on. Then if I put in x as pc over mc squared, I get that k is the classical kinetic energy, and then I have to add in a few corrections, and of course if I want to get it exact, I have to add an infinite number of corrections. But what we're going to find is that these corrections become extremely small extremely quickly. So, for example, K0 is the kinetic energy of the electron. That has the same order of magnitude as the total energy of the electron. It's about 13.6 electron volts in the ground state, something like that. So we'll call it 10 electron volts. And then K1, the first correction to the kinetic energy, goes like p squared over m cubed c squared, and then the next correction goes like p to the 6th. So let's look at the size of these things. K0 is around 10 electron volts. mc squared is like 500,000 electron volts. And so the ratio of K1 to K0 is the same as the ratio of the kinetic energy of the electron classically to the rest energy. And that kind of makes some intuitive sense. Then notice that because k squared goes like p to the 6th, the ratio between k2 and k1, the second order correction and the first order correction, is also order of magnitude k0 over mc squared. But what is k0 over mc squared? Well, it's something like 10 to the negative 5. And so what that means is that k1 is about 1 part in 100,000 of the classical kinetic energy, and K2 is something like a part in 100,000, 2 parts in 100,000 of that. So we're going to worry about the first correction, but we're not going to worry about the second one because it's 100,000 times smaller, or 50,000 times smaller. So we'll worry about K1. We're going to forget about K2. So let's throw K2 out and focus on K1. K1 is p squared, basically, over mc squared. Of course, there's another m squared in there. So we want the expectation value of K1 in the state of the electron, the first order correction of perturbation theory, the first order correction to the energy, is the expectation value of the perturbation in the state that you're interested in. And so what we're after is the expectation value of p to the 4th, essentially, in any particular state of the hydrogen atom. Now the interesting thing is p to the 4th, you could think of it as the original Hamiltonian, the unperturbed Hamiltonian, plus the negative of the potential energy. Now remember, the original unperturbed Hamiltonian is the kinetic energy plus the potential energy. So if I subtract the potential energy, I've just got the the kinetic energy, which goes like p squared. And so h0 minus the potential energy squared is going to be proportional to p to the fourth. And why is that useful? It's useful because I can use it to figure out a way to compute the matrix elements of p to the fourth using the known matrix elements of the original Hamiltonian and the potential energy. So that's what we're going to do. So we square that thing. We're going to get three terms. We're going to get an h0 squared, we're going to get an h0 divided by r, and we're going to get a 1 over r squared. So the h0 squared is easy because that's just the square of the unperturbed energy. Then the next thing we have to worry about is the h0 times 1 over r. But of course h0 is just the unperturbed energy, and so that reduces to the unperturbed energy times the expectation value of 1 over r. But of course there's a thing called the virial theorem that allows you to know that the expectation value of the potential energy is minus twice the expectation value of the kinetic energy. You might have done the virial theorem when you were taking your analytical dynamics class. But anyway, you can look it up. It's a neat little theorem. The relationship between kinetic and potential energy has to do with the power of r in the potential. And for potentials that go like 1 over r, it turns out the potential energy is minus twice the kinetic energy, something like that. Anyway, there you can easily calculate this just using the virial theorem. You don't even have to do an integral. But the last term is the 1 over r squared term, and for that you do need to do an integral. The integral turns out to be like this. It has an L plus a half in the denominator and an n cubed down there. There is a complete treatment of all this stuff in the Hans Bethe and Edwin Salpeter quantum mechanics, 1 and 2 electron atoms. You can look that up if you want to, but basically I'm just telling you the answer. I don't expect you to actually work that out at this point. And when you plug all that back in, what you get is the expectation value of the perturbation. When you put all three terms back together, it looks like this. Notice it only depends on L. So if you know L, then you can work out the expectation value of the perturbation. Okay. Now let's go ahead and talk about the spin-orbit coupling. The spin-orbit coupling is, remember I mentioned that the magnetic field that the spin magnetic moment, that the electron's magnetic moment sees, has to do with the magnetic field produced in the frame of reference of the electron by the electrostatic field of the proton in the laboratory. So, and that Hamiltonian, of course, is minus the magnetic moment dotted into the magnetic field. So this is a formula you probably learned in your electrodynamics class. I'm just going to write down the answer. I'm working on a explanation of this effect that's a little more detailed than what you see in the book. The book basically goes into the frame of reference of the electron and treats the proton as a Biot-Savart current that produces a magnetic field at the location of the electron. But then you have to do all kinds of monkey business to get back to the right answer. Anyway, I'm working on something. I don't know if I'll be able to work it out, but anyway, you can read what Griffiths has to say. You can just take my word for it. But there is a correction to the energy. The perturbation is proportional to S because the magnetic moment depends on S, and it's proportional to L because the Biot-Savart magnetic field from the proton depends on L. Or if you like, the magnetic field observed by the electron due to the Lorentz transformed electrostatic field of the proton depends on L. So you end up with the dot product of S and L, and that is the perturbation. Now the thing is, the total angular momentum J is L plus S, and what we're going to find out is that while L no longer commutes with the Hamiltonian, does not commute with the perturbation, and S does not commute with the perturbation, that the sum of the two, J, does happen to commute with the perturbation. Let's look at that. If you calculate the commutator of L dot S and L, you do not get 0. The commutator of L dot S and L almost magically turns out to be the cross product of L and S. And the commutator of L dot S and S turns out to be the cross product of S and L. But if you calculate the commutator of L dot S and J, that's the commutator of L dot S and L plus the commutator of L dot S and S. And if you know anything about cross products, you know that if you take the cross product of A cross B, it's the negative of the cross product of B cross A. Well, that's also true of L and S. So if you add those two cross products together, guess what you get? Nothing. So what that means is, while L dot S does not commute with L, and L dot S does not commute with S, L dot S does commute with their sum, which is J. So what does that mean? Remember that the time rate of change of an expectation value of an operator is the commutator of that operator with the Hamiltonian. If the operator commutes with the Hamiltonian, it means that it is a conserved, its eigenvalues, if you measure it, it doesn't change in time. So J is a conserved quantity. J does not change in time. But L and S do not commute with the perturbation. Therefore, under the influence of this perturbation, neither L nor S are conserved. They change in time. Now, you can also show that L dot S does commute with the length of L, the magnitude of L, and L dot S does commute with the magnitude of S. So the magnitude of L and the magnitude of S don't change, but the individual components of L and S do change. Having said that, the sum of L and S does not change, and the magnitude of the sum, obviously, if the sum doesn't change, then the magnitude of the sum doesn't change. And so we get J squared, L squared, and S squared are all conserved. J is conserved, but L and S alone, individually, are not conserved. Now, what is J squared? J squared is the dot product of L plus S with itself. But if you work that out, that's the magnitude of L squared plus the magnitude of S squared plus twice the dot product of L and S. And we can use that as a trick to figure out what L dot S is in terms of the magnitudes. L dot S is half of J squared minus L squared minus S squared. This is a really important trick. We use it all the time if we're doing angular momentum calculations, and so it's sort of burn that into your memory banks or whatever. But the point is, since the spin-orbit coupling perturbation is proportional to L dot S, we can use that to work out the size of this guy. We do need the expectation value of 1 over r cubed, because you can see that it depends on 1 over r cubed. And so when the smoke clears and you put everything together, you get the following result, that the perturbation, the first order perturbation energy of the spin-orbit coupling goes like J times J plus 1 minus L times L plus 1 minus S times S plus 1. That's just the L dot S term. Of course, S is a half, so S times S plus 1 is 3/4. And downstairs, we've got L times L plus a half times L plus 1. That comes from the expectation value of 1 over r cubed. And that's how the whole thing turns out. You can simplify that. If you add the spin-orbit coupling correction and the relativistic correction together, it turns out they have roughly the same order of magnitude. The whole thing ends up depending only on J, which is sort of amazing. And if we have time, we can work some of that out. It's a little tedious, but it is possible to do it. And you can see how it turns out. But the total fine structure, this is the so-called fine structure correction. It's a combination of the spin-orbit coupling correction and the relativistic correction. And it ends up only depending on J, the J quantum number. The very last thing I want to discuss is the Zeeman effect. And the Zeeman effect is what you get when you put a hydrogen atom, or any atom basically, in a magnetic field. You get a Hamiltonian that comes from two pieces. There's the magnetic moment the electron has as a consequence of its spin, plus the magnetic moment that it has as a consequence of its orbital angular momentum. You add those two together, and you dot them into the external magnetic field. So this is another mu dot B thing. But this time the B isn't internal. It's not built into the hydrogen atom like the spin-orbit coupling, but it's actually something in the laboratory. You have a magnet in the laboratory, and you stick the atom in the magnetic field, and you look at what happens to its energy levels. And the answer is the energy levels change. Now here's the thing. The spin magnetic moment is E over m times the spin of the electron. The orbital angular momentum magnetic moment is half of E over m times the orbital angular momentum. So what that means is when you put in all that stuff and you calculate the perturbation, you get L plus twice S. Now here's the thing. We found out, due to the spin-orbit coupling, that L plus S is conserved. J is conserved. But this Hamiltonian is not equal to J, or not proportional to J. It's proportional to L plus 2S. But I can rewrite L plus 2S as J plus S. And if I have a weak magnetic field where the perturbation due to the Zeeman effect, or due to the external magnetic field, is much smaller than the fine structure, in other words, much smaller than the spin-orbit part, then I can treat the Zeeman effect as kind of a perturbation of the solution we got for the spin-orbit situation. So we're going to be talking about very weak fields for the moment, and in that case, J is a good quantum number. J is conserved because J is conserved in the spin-orbit coupling, and it's much larger than the energy that we're talking about calculating. And so the idea is you can think of J as being good and S as varying. But the thing is, so parts of S are going to average out to 0, and parts of S are going to be are going to have a finite average contribution, but we got to figure out which parts we need to worry about. So the idea is J, the total angular momentum, is conserved. Neither L nor S are conserved, and so you can think of L and S as sort of processing around the vector J. And in the presence of the magnetic field, of course, the vector J is going to process around the magnetic field, but S and L process around J. So the precession of S and L around J is due to the spin-orbit coupling. The precession of J about the Z direction is the Zeeman effect, but it's very slow compared to the precession of S and L around J. And so what we end up with is that the only piece of S that survives is the projection of S in the J direction. How do you calculate the projection of a vector in another? Well, you take the dot product of the vector with the direction you're interested in, and you multiply by the direction you're interested in. And that's, of course, a unit vector in the direction you're interested in. And so if we write that out for S and J, if we want to know what's the projection of S along the J direction, we end up with this expression. And if we put all that in, we get the expectation value of J plus S is it's J, and then we have to add in just the projection of S along the J direction. We're going to work this out as a board work problem today if we have time, but I can tell you that the answer turns out to be that the Zeeman effect, perturbation energy, is proportional to the magnetic field. It's proportional to the Z component of J, and to the this thing called the Landé factor, which we'll work out on the board today. And it's also, of course, in the book. You can see how that turns out. But that's all for this time. Next time, we're going to go ahead and look at the strong field limit. What happens if the Zeeman field is much greater than the internal field, so that the Zeeman Hamiltonian is much greater than the spin-orbit coupling Hamiltonian? And then what about if the two perturbations are roughly the same order of magnitude? How do we handle that? That turns out to be a little bit of a mess, but we need to see how it's done, and so we'll do that next time.